In Chapter 1, we learned how to describe histograms, a graph that shows the frequency of data using intervals of equal size. The histograms shown represent the data found from 10 trials of randomly selecting 10 Skittles out of the bag, making sure to replace them so the probability is the same every time. I then split the data by color, producing the graphs shown. In order to describe a histogram, we learned to use the acronym SOX. This stands for Shape, Outliers, Center, and Spread. Starting with shape, when looking at this graph, you can see that it looks relatively symmetrical, kind of like a bell curve. But the gap in the data suggests there might be a slight skew to the right since the tail of the graph goes off to the right. Skipping to center, you want to look at the mean and the median. For this set of data, the mean and the median is 4. The mean is a non-resistant value, meaning that it is greatly affected by outliers, and the median is resistant. Since both of these values are the same, it indicates that there is no skew in the data. Then with the spread, you are looking at the variability of the data, or how spread out it is. Compared to the other graphs, this histogram is relatively spread out. This can also be shown by the standard deviation of the data. Going back to outliers, this graph appears to have one possible outlier at 8. You can check if the value is an actual outlier using the 1.5 IQR rule. The IQR is the interquartile range, the difference between the first and third quartiles. For this data set, Q1 is 3, Q3 is 5, so the IQR is 2. To set boundaries for outliers, you then compute Q1 minus 1.5 IQR and Q3 plus 1.5 IQR. For this data, the boundaries are 0 and 8, which happen to be right on the edge of the data, but since no data points go beyond the boundaries, there are no outliers.
So for Chapter 2, it mainly dealt with z-scores. So the z-score is equal to whatever value minus the mean divided by the standard deviation. So for our data, the mean was 27.94 seconds, and the standard deviation was 14.8 seconds. And this was for the boiling water and the Skittles experiment. So the first example is what proportion of the sample will dissolve in under 10 seconds. So first you find the z-score, and you get negative 1.21. And then you use the z-score standard table, and you find that this value corresponds to a proportion of 0.1131. So because it's asking for under 10 seconds, so wherever 10 is, you're looking for the proportion under, then this would just be your answer.
In Chapter 3, we learned how to use a scatter plot to examine the relationship between explanatory and response variables. The scatter plot shown here represents the data I collected in an experiment in which I measured how the quantity of Skittles in a mug affects the amount of time it takes for those Skittles to completely turn white or lose their color coding. In this experiment, the explanatory variable is the number of Skittles in the mug, so it is plotted on the x-axis. The y variable, or the response variable, is the time for the Skittles to turn white or completely lose their color, measured in seconds, so it is plotted on the y-axis. To make the relationship between the two variables easier to see, we can use a least squares regression line, as shown here. The equation for this least squares regression line is predicted y value equals 24.94 plus 0.34x. The correlation coefficient for this distribution is only 0.114, which suggests that the data has a very weak linear relationship. Because of that, we can assume that a linear model might not be the best model to use in this case. However, if it was an appropriate model, we could use the least squares regression line to calculate the predicted y values based on x values. For example, if we knew that the x value was 5, we could predict that the y value would be about 20 by using our scatter plot.